Hi all. For this last bit, I'd just like to work through some examples that require the new rules that we've learned. Really, the applications stay the same. We'll work on some more advanced applications in Chapter 3, but for these, we'll still be finding tangent lines, finding rates of change, finding second derivatives, but it can feel like you're supposed to do something totally different. The truth is just that when you get to the derivative taking step, you don't have to go back to the limit definition anymore. You can use your shortcuts. Okay, so the first one that I have is just directions to find the slope of the tangent line to h of z equals the square root of z plus 1 over z at the point where z equals 4. So we should know, hopefully, that slope of tangent equals derivative, and we specifically want the derivative when z equals 4. So we're trying to find h prime of 4. That needs to be a two-step process. You need to find a derivative formula, and then you need to plug 4 in. So h prime of z maybe requires just a tiny little bit of algebra to get it set up. So the algebra step is to say that the function can be written as z to the 1/2 plus z to the -1. So we need to be good with those exponents, or things are going to be a little harder for us. There are no constant multiples in this, but it is a sum, so that just means that we'll look at the two totally separately. So first we focus in on z to the 1/2 power, which is a power rule. The base is the variable, which means the power comes down. If you're ever dropping variables down, you're doing something wrong. The variable should be sitting in the base for a power rule. The new power is 1/2 minus 1, or -1/2. The plus just sticks around. The derivative of z to the -1, the -1 drops down to the front. The new power is -1 minus 1, which is -2. And we can clean that up a little. I would write that as 1 over 2 z to the 1/2, or even 1 over 2 root z. If you're a good memorizer, it might be worth just memorizing that the derivative of the square root of z is 1 over 2 root z, because that one crops up so much, but it's not required. You can always do it with a power rule, but that's kind of a handy one to just jump straight into sometimes. And then, because it's a -1 out in front, we'll make that a minus 1 over z squared. So I have my derivative formula. Now to find the slope of the tangent line, I can plug in any z value I want, and it will give me the corresponding slope. So if I plug in 4, I get 1 over 2 root 4 minus 1 over 4 squared. Root 4 is 2, so I really have 1/4 minus 1/16. So I'll need a common denominator. So 4/16 minus 1/16 is 3/16. If this had asked me for the equation for the tangent line, keep watching that wording, I would then have to go back to the original function and find a point as well, and I would be able to put that together and write an equation. So you should be able to do either. It's just a little easier to find the slope than it used to be. Hopefully it's easier. All right, the second one is actually a word problem. We are told that a population of cells is growing according to this formula. It kind of ran across lines there, where t is measured in days. So it's number of cells and number of days. We are supposed to find the instantaneous rate, so that's going to be derivative, at which the population is growing on day 4. So this is another t equals 4. And we're supposed to give units in our answer. So again, what's new here is that to find p prime of t, we don't have to go back to limits. We've recognized some patterns that allow us to jump straight to what the answer will look like. So what I do see for my shortcuts is that there's a sum, so I can look at this as two separate pieces. In the first piece, that looks a little messy with the decimal sneaking in on us, but it's not any harder than any other exponential function. The 2 is a constant multiple, so it will just come along for the ride. Because 1.37 to the t has the t in the variable, we'll use an exponential shortcut. That will be 1.37 to the t multiplied by the natural log of your base, which is 1.37. The plus then just carries through from the sum. But the derivative of 32, that's a lonely constant, not a constant multiple, so it's really just 0. So you don't have to write that, but I just want to keep writing it for now. I'll drop it in a little bit here. We were asked what's happening, what's the instantaneous rate of change on day 4. So we plug in 4 for our t value. We get 2 times 1.37 to the 4 times the natural log of 1.37, which is entirely a technology question. And my technology crunching gave me about 2.22 if I round to that decimal place. And we're supposed to include units on our answer. So we had the number of cells was a function of the number of days. So I would say this is a slope. It will be cells per day. So the population is increasing by about 2.22 cells per day on day 4. Not very fast so far. It's exponential, so eventually it will get fast. Okay, there's a second part to this one. The second part says, is the population growing at an increasing rate or growing at a decreasing rate? So this increasing rate, decreasing rate, that's not just a question about is it growing or decaying. We're assuming it's growing. That's already expressed. Is it speeding up or slowing down? This is a second derivative question. So this is a p double prime question. So we need to find p double prime, which means I'd like to just, excuse me, reorganize my p prime a little bit, because p double prime is the derivative of p prime. So I'm going to take this and 1.37 to the t. Let me erase my scribblings here for now. And I need to take its derivative again using shortcuts. So this is basically a full reset. It doesn't matter what we started with. It only matters what p prime is. We pretend like that's the original function and we apply shortcuts in the exact same way. This one can look really scary to people, but the truth is that all of this is just a tricky constant. There is no variable in there. There's no variable attached to any of that except for the multiply by. So this is a constant multiplied by a function of t, which means all of that just comes along for the ride. And we really just need to focus on the 1.37 to the t that's remaining. And the derivative of 1.37 to the t is itself times the natural log of its base. So basically, as you continue taking derivatives of exponential functions, every time you do it, you'll pop out another natural log. And if we wanted the simplified version, we're going to plug in, so it maybe doesn't matter too much. But if we wanted a little bit simpler version of that, you could write that as the natural log of 1.37 squared times 1.37 to the t. And don't lose the 2 out in front. We were asking what's happening on day 4. So back to our technology to plug 4 into the second derivative. And I got 0.698, which you can round how you please there, because really the question we got was about positive or negative and not really about exactly how big that was. So if your second derivative is positive, that means that the graph is concave up, and concave up means it's growing at an increasing rate. The slopes are getting bigger, so this is an increasing rate. So again, remember, if you get any questions about concavity or whether slopes are getting bigger or smaller, that is a second derivative question. Okay, one more, and then if you're printing these out, there's a vocab list for you at the bottom and a list of these shortcuts that we just went through. The equation for the tangent line. Okay, so here we have to do a full equation for a tangent line. So we'll take p prime of a because we want to get a slope, right? Really, we want to get the slope at -1. So to get the equation for a tangent line, you'll need p prime of -1 to get the slope, and you'll need p of -1 to get the point. So p prime of a, this is a bunch of addition, subtraction. So we can split that up into pieces. 3a to the 4th. The 3 is a constant multiple, so it just sticks around. The derivative of a to the 4th is 4a cubed. The minus sign that comes next is just going to carry through, as will the 2, which is also a constant multiple. The derivative of a cubed, that's another power rule. The 3 drops down. The new power is 3 minus 1. And then our plus carries through again. And we're on 7a squared. So 7 is a constant multiple. The a squared will have the 2 drop down. The new power will be 1. And subtraction again. The derivative of a is just 1. And then finally, the derivative of 12. 12 is a lonely constant, so that's 0. So to clean it up just a tiny bit, I get 12a cubed minus 6a squared plus 14a. Minus 1, I almost lost it. Notice that now that we have this power rule, you can start to see some patterns. The derivative of a 4th degree polynomial will always be a cubic. The derivative of a cubic will always be quadratic. The derivative of a quadratic will always be linear. And if you think back to when we were trying to sketch derivatives, this starts to give us some hints. Even if we don't know exactly what the formula is, we have some ideas of what the shapes might be. Okay, so I need p prime of negative 1, which is going to be 12 times negative 1 cubed is negative 1. So it's going to be negative 12 minus 6 times negative 1 squared, which is 1, plus 14 times negative 1, so negative 14, and then minus 1. What do I see there? Negative 20. I think I see a negative 33. And that is my slope. I also need the p of negative 1 to get my point. That's all the way back to the original function. So when I plug a negative 1 in there, 3 times negative 1 to the 4th is just 3. Negative 1 to the 4th is positive. Minus 2 times negative 1 cubed, which is negative still, so that becomes a plus. Plus 7 times negative 1 squared. Negative 1 squared is 1. Minus negative 1 becomes plus 1. Plus 12. I think I'm getting 25. So let's see if we can sneak this in over here. I have the point negative 125. So we can take y minus 25 equals my slope, negative 33, times, what was my variable? A minus negative 1. So a plus 1. Which means y is negative 33a minus 33 plus 25, or final answer, y equals negative 33a minus 8. Okay, so those are, again, same kind of examples we were doing, but new ways to get the answer. So just let me know if any of those mix you up. Otherwise, hopefully you'll find that they start to make more and more sense.